So this is geometry, lesson 2.6, and we're going to be diving into polygons and being very specific about some definitions so that we're clear, that we know exactly what it is, not just because we've always known what a triangle is, but because we've given it a proper definition. So the big idea here says some unions of segments in the plane are polygons. And the number of segments classifies a polygon as a triangle, quadrilateral, pentagon, and so on. So I've started off the notes here with some things that are not polygons. And these all are unions of three segments or three lines. And so if I asked you to come up with the definition of a triangle, you might say a three-sided shape, but shape probably not well defined. You might even say the union of three segments. Okay, but that's still not specific enough, even though you're starting to now be on the right track. All four of these are unions of three segments that are not triangles. You might say it's the union of three segments that are connected. Well, this one's connected, this one's connected, this one's connected. These aren't, okay? So we've improved on this one. You might say that they need to intersect at least two of them, because if you look at letter C, these extra lines out here, they're not connected, so they only intersect one other segment. So you might say it needs to intersect at least two. And now we're looking at B and D. We've got three segments, and they're all intersecting two of the other segments. Okay, but we haven't really defined it yet. So what are we looking for here? So definition of a polygon. It's the union of segments, obviously, such that each segment intersects exactly two others. Okay, so far, this definition, B and D, would be considered polygons, and obviously they're not. And then here's the key point, one at each of its endpoints. So if we look at letter D, that's a union of segments, and each segment intersects exactly two others. That's happening here. Okay, this segment intersects 1, 2. This segment intersects 1, 2, and this segment, I don't know why I'm having trouble with that word, intersects exactly two others. So we have to be a little more specific. The intersection has to be at each of the endpoints. So the intersection has to occur at the end of the segment, and then we have a polygon. Okay, so now we've given it a good definition. All right, now we're going to just talk about some key vocabulary words for these polygons. Obviously, we know what the sides of a shape look like, what they are. I think we would all be able to identify those. So specifically, those are the segments that make up a polygon. So a side, you would write it as something like segment PO or segment NG. And since it's a segment and not array, the order that you put those letters doesn't matter. You could say GN or OP. It's important that we know what this word means, vertices. Those are actually the points, the endpoints of these segments. So the endpoints of the sides are your vertices. And if we're talking about one specifically, just one, that's called your vertex. So all of them, plural form is vertices. One specifically, that's vertex P, that's vertex O, but these are the vertices, okay? We need to know this word, adjacent. Sometimes it's called consecutive. That basically means next to each other. Okay, so when we name these, if I was going to name this polygon, we can start with any letter we want. We don't have to start with P, we don't have to start with O. When we name this, we can start with any of these letters, but we do need to go around the outside with adjacent or consecutive vertices as we name it. For instance, I could name this P, O, L, Y, G, N. So I made my way around the outside this way. I could have started with G and gone the other direction. Y, L, O, P, n, okay? But as I make my way around, I am using adjacent vertices, the ones that are endpoints of a side. So from G, if I'm going to name it, I either got to go to N or I got to go to Y. I cannot call this G, L, P, Y, O, N all over the place like that. Adjacent sides, same idea. They're the sides that are next to each other, also sometimes called consecutive. But if we're being specific using geometric terms, they are the sides that share an endpoint. So YL and GY are adjacent sides, and they share the endpoint Y, and that's technically why they're adjacent. But they would be the ones next to each other. So GY all the way across the shape from PO, those would not be adjacent sides. So they're going to be connected at an endpoint. And then a diagonal, so now we're going to talk about the vertices that are not adjacent. It's a segment connecting non-consecutive vertices or non-adjacent. And so if we started at G, G has two adjacent vertices, N and Y, depending if I'm going clockwise or counterclockwise. I can go either way. So from G, I have N and I have Y. Both are consecutive vertices or adjacent vertices. Now, a diagonal vertice, we probably would think of O and L, but P is as well. And obviously this is a non-convex shape. We have to go on the outside here to get from G to P, so this would be considered non-convex. We've talked about shading in those regions, and that has to show if that region is convex or not. When we're talking specifically about polygons being convex or not, they don't always have to be shaded. We're just looking at the diagonal vertices. And if I have to go on the outside of the shape, it's non-convex, like we've studied. And if all of them are on the inside of the shape, then that is convex. Okay, so a diagonal doesn't have to cut across the shape. A lot of people would look at GP and say that's not diagonal. Diagonal has to go across the shape. Well, diagonal just means you're going from one vertice to another and they're not adjacent. So the only adjacent vertices to G is N and Y. So diagonal vertices are all of the other ones. They're non-consecutive. All right, so some key vocabulary words there. Continuing on that trend here, we're going to look at specific types of polygons. So if you're reading a question and it refers to an n-gon like that, n is, instead of x or y, n is the variable they use for number of sides usually. And so if they're not telling you how many sides there are, it might be something you have to figure out in that problem. They're going to call it an n-gon. And so the first time you see that, that just looks weird and you're like, what's an n-gon? So that's just a variable. We don't know how many sides. We know it's a polygon. It's got multiple sides connected at the endpoints. Okay, but we don't know what it is. So that's the variable. Now, some specific types that we do need to know. We all know a triangle has three sides. If I asked you what's a four-sided polygon, some of you might say rectangle, some of you might say square. There's other ones. There's trapezoids, rhombus, and you've covered all those in some of your pre-algebra stuff. But the term for a four-sided polygon is quadrilateral, and that should make sense. And you've heard that term before. Quad means four. Okay, so four-sided polygon is a quadrilateral. There's all different types, but the general term for a four-sided polygon is quadrilateral. 5 sides, pentagon. 6 sides, hexagon. 7 sides, heptagon. 8 sides, octagon. 9 sides, nonagon. And then some of these ones that you may not have heard, you probably heard decagon before for 10, but 12, dodecagon. And once you get past that, they do technically have names, and you can Google them, and some of them are kind of weird. But those are the ones that we really need to know the names of that will actually use it. If there was a 13, they would probably just say 13 gone like that, or 20 gone. They technically do have names. Again, you could Google it and look them up. But in terms of what you're going to see in the book and in a problem. If it's not one of these key ones, they're just going to write it like that for how many sides there are. All right, so with these polygons, they're in a plane, and because they're connected at their endpoints, they create two regions. This should make sense. You've got your interior region, and you've got your exterior region. And so here, shaded in, is the polygonal region A, B, C, D, E. So if we name this region, not just the polygon, so this is your 1, 2, 3, 4, 5-sided polygon. So this is a pentagon. This would be a non-convex. We name it by its vertices. We go around the outside, A, B, C, D, E. They're adjacent. You could go the other way, A, E, D, C, B, and you don't even have to start at A. You could call this polygon D, C, B, A, E. Okay, so that's how we name the polygon, and we also can name the actual region that's inside of it. So the polygonal region is still named by the vertices that form that polygon, but we've got the interior region and we've got the exterior region. I think that makes sense. All right, and lastly, we're going to look at specific types of triangles. We need to know the difference between these. So a scalene triangle has no sides that are equal. Every side has a different length. An isosceles triangle, and I know you've heard these terms before, has two sides that are equal in length. It's important that we understand these markings mean equal. Okay, so since these two sides have those little markings, they're equal. And since the third side does not have that marking, we cannot assume that it's the same as these two. So just these two are equal and this one's different. Okay, so an isosceles triangle has two. Now, it's important to understand that it's not exactly two. It could be three, but it's just saying there are two sides that are equal. Scalene, no sides equal. Isosceles means there's two, and a specific type of isosceles triangle is an equilateral triangle where all three sides are equal. So notice they've got those markings. Now, you see these markings have two little lines. Sometimes that's how they're marked. They could have three. And what you do is you find the matching ones. So if we had a bigger shape, let's just connect it like that. Let's say these two sides were equal. It might be marked like this. Well, if these two sides over here were equal, but they're not equal to these ones, so let's say this was 3 and 3. Let's say these both were 5. So I need to show, if I didn't have the numbers, that these are equal to each other, but not equal to these. So I have to use a different marking. So you'll see it like that. Two lines showing you that these are equal, one showing that these are equal. So the fact here that they all have two, they all could have had one, they all could have had four little lines. But equilateral means all three sides are equal to each other. So over here, this is called a hierarchy. So at the top we have all figures. A specific type of figure is a polygon, because a figure can be a line, can be an array. We've studied those. But now we've got these segments that are connected at the endpoints. Those are called polygons. We talked about there's all these different types of polygons. One specific type is a triangle. And triangles can be classified as two things, scalene or isosceles. No sides equal, two sides equal. Notice that it's not split into three pieces, into these three things. Equilateral is actually a part of the isosceles family. Because I would ask you, does an equilateral triangle have two equal sides? Yes, it does. And you would say, no, it has three. But are two sides equal? Yes, two sides are equal in an equilateral triangle. So it is technically isosceles. So triangles get split into scalene and isosceles, and then a special type of isosceles. So not only are two sides equal, now three sides are equal. That's an equilateral triangle. And that's what this example says. According to the hierarchy, an equilateral triangle is a special type of what figures? So equilateral could fall under what categories? Is it isosceles? Yes. Is it a triangle? Yes. Is it a polygon? Yes. Is it a figure? Yes. So when you find an equilateral triangle and you go up on the hierarchy, an equilateral triangle is an isosceles triangle. It's a triangle. It's a polygon, and it's a figure. So we need to know it's a subset of all of those here in the hierarchy.